Okay, so I don't care about you writing this down, certainly don't care about you remembering it. So it's complicated. All right, what is this to begin with? It's a probability function. So now we are looking at a distribution as a function of speed, okay? And here I'm actually specifically talking about speed rather than velocity. Of course, one's a scalar, one's a vector. And this distribution does look different depending on whether we're talking about a scalar or vector quantity. All right, so it's a probability function. Let's try and parse it and break it down and see if we can get to the essence of what's going on. Okay, so a bunch of constants, usually not interesting for us. Where are the key variables? So our key variables, probably speed and temperature. Otherwise, we're basically looking at constants aside from the molar mass. So, okay, not a trivial dependence, but maybe the v dependence is the one we're most interested in. So we have a v squared dependence here, and then an e to the minus something v squared here, okay? So, roughly speaking, we can expect something that is small at extrema and large somewhere in the middle of a speed distribution, okay? So that's the main thing I want to take away from this, otherwise it's way too complicated. And so, in fact, typically, visually, that's exactly what I said. It's something that's small at extrema and peaks somewhere in the middle. And if you want to plug in something of this form into a plotting engine, you're going to see something.
Oh my gosh. No, it's because like during chemistry, like we learn about these graphs. They're like, okay, if the like speed is like, you know, larger than, it's like, this makes sense now. It's like there's a mathematical equation to describe this, like, I've seen this before.
Okay.
Yes.
Sorry, that was a little bit of a little surprise on my part. Oh my god. What's going on? Okay, well that's good, I think. Sorry, I'm not quite sure what to do.
Now I'm going to watch the YouTube video.
A little comic relief from the Maxwell speed distribution.
No, but like in chemistry, we have these like one thing. It's like a very qualitative feature of like particles where you have to like know their kinetic speed distribution. And it's like, okay, you just memorize it. That's cool. Like if a particle is like, I forget what it is exactly, but it's basically like if it has a certain property, its speed changes or something. But then like this actually shows like why that's true. There's a mathematical equation to describe it.
Okay. Good. Just a kind of sort of snotty footnote here. You know, chemistry often strikes me a lot about memorizing things and trying to remember things. Physics hopefully is not that ever, and it's more about, you know, trying to just get to the essence of things, and at least here, at least a qualitative understanding. Sorry.
I was just wondering, is the equation empirically determined, or
It's not. So it's derived from primarily statistical physics calculations. So it's definitely calculated. So in that sense, it's exact. Okay. So, having had a little bit of a revelation here, let's see what we can do with it. So as with any probability distribution, we can take this and calculate some particular, let me say, statistical values from this distribution.
Okay, so like I have a picture. Like no, here I don't know how to do this, but like
You can just say it.
okay, so basically it's a graph of the number of molecules versus the molecular speed, and it's like something that you have to know in chemistry, where it's like at different temperatures you get like different like speeds, but it's the same thing basically, right?
But is this, how does this relate to like, because I think the graph he's talking about, it's like they're different, like they're different lines at different temperatures, and you see as this temperature increases.
No, it's all right. It's all right. We'll talk about it offline.
Okay.
But I just want to hear your footnote comment.
But it's because I mean I believe the graph he's talking about, it's like not exactly the same axes, but it's like different temperatures, and you see as like the temperatures go, it's like a more spread out velocity. So is that the same thing, I guess? Like you just see that there's a more spread out velocity.
Yeah, I mean, again, all you need to do here is take a simple plotting engine. There are two parameters really of interest here. Once you first M, just plot for a given t, for example, what this looks like in terms of a distribution of speed. Or I think a little bit alluding to what you want to say is, you know, instead play around with the temperature variable. How does this change? Okay. So there's no deep magic in here. Okay? All right. So as with any probability function like this or distribution, we're gonna, and again, I'm rarely going to ask you to do any calculations because it's such a tricky function. But I just want you to know it can be done, obviously, and what the results are that drop out of this. Okay, so first off, what does this tell us? So we can learn about the fraction of constituents between certain velocity windows.
Not even anybody I know.
Start of something beautiful. Okay. I'm sorry, I don't know why today's getting a little giddy. So obviously the fraction of constituents between certain velocity intervals is simply that. We're integrating over this. And of course, the fraction over the entire spectrum is 1. So we normalize this, of course, with the usual normalization, which is to say that the integral from 0 to infinity of this guy better be 1. So there's our normalization criterion. Okay, what's most useful is the three things I'm about to derive, not in class, because we don't have the math to, most of us, to do this. But three particular useful results that come from this. So here they are. Okay, so 1, the average speed. If you use the integral here. So just a little bit of a reminder of how we would do these types of calculations. So we would simply integrate over the entire distribution, multiplying the function itself by its value at every point. That's going to, by definition, give us the average, okay? So again, we're not going to do this calculation, but if you do, the result that you get is 8RT over pi n. I'm not going to write these in molecular basis. At this point, you know you can switch R for K and N for little n if you wish and get the same thing on a molecular basis. So that's the average speed. Okay, now to come back to Joseph's question, RMS, here it is again. It's the square root of the average of the squares, so specifically defined. I'm not going to write this out. It turns out that the result here is 3 square root of 3 RT over n. Note this is 8 over pi, this is just 3. And then lastly, the most probable speed, that's called the mode in old language. Most probable speed, again, no derivation, is the square root of 2 RT over n. Okay, quick reference back to this image over on the right-hand side. Just so the most probable speed, what did I say, square root of 2RT over big M. Then a little above this, depending on our parameters, temperature, the average speed, and a little above that, the RMS speed. Okay, is this of great importance? Not particularly. I just want you to be obvious that these things can be calculated if you have the math machinery to do it, and you're generally going to get this ranking in terms of common statistical measures of the speeds of our constituents, okay? All right, what's the point of all of this? Of course, there is a distribution. We learned something early on today just by focusing on RMS and average. There is a distribution. Once we know its form, which we're not going to derive, we can use this to calculate all sorts of detailed statistical properties of our ideal gas. That's pretty much all I think I want you to know about this. Just to reiterate that with this dependence, if we go to higher temperatures, we expect that distribution to push outwards, okay? Most of all, I want you to build physical intuition on this. We've got higher temperature, we've got higher speeds, then the distribution goes out. We've got larger masses. How does this go with mass? Maybe not so obvious from that form, but again, you kind of know just on basic physical behaviors. If I have increasing mass constituents, which direction would you expect that velocity distribution to shift? To the left, right? And so, okay, right. Good. Questions? Yeah.
Why is having these three different?
Why is it useful?
Yeah.
Yeah, fair question. We're not going to make use of this, okay?
Wait, what?
We're really not. We're mostly caring about the stuff that came directly from our kinetic theory model and the relationship of RMS speed, pressure, and temperature. In this course, we're not going to make much use of this. Obviously, if you are interested in more realistic gases, then knowing this distribution may be important. If you're interested in various practical applications, knowing these things are important. So yes, it's not uninteresting, it's not unimportant, but for our purposes, in the sort of relatively limited things we're doing with ideal gases, we don't care much about this. But I just want you to understand where it came from, okay? In case you see it later on. All right. I'm going to ask you guys to do a quick calculation with your neighbors. It has to do with mean free path. So let me just set up a rather simple problem. I just want you to do a little bit of calculation for 5 minutes, and then we're going to turn our attention for the remainder of the morning to come back to specific heats.
And you know what it is? It's a it's like a two-dimensional equation. There's multiple inputs.
Okay, stay to begin with.
This makes sense now. It's like a real thing. It's not
So,
like fake balloon science.
Gas flow through a pipe or a hose. So a statement to begin with and then a calculation from all of you. If the hose diameter is much larger than the mean free path, then we can basically treat our gas as a fluid. But by contrast, if the diameter is less, then we need to kind of look at these as individual free molecules. So this is saying treat the constituents individually. So can I think of, since you asked very appropriately what use is this, why might this be of interest? lots of possible applications I can think of, engineering type applications where this sort of behavior might be important. So it's basically just going to be a calculation of figuring out what the mean-free path of some particular gas and certain criteria are. But you can imagine the uppercase being true if we've got some kind of aperture, some kind of system which has a characteristic size that's much larger than the mean-free path of our gas, then it's very much going to behave like a fluid. But by contrast, if things are turned around, then we're basically looking things at individual constituent level. So let me ask you to do the following calculation. Okay, so here's the calculation. For a hose of diameter 1 centimeter, question is, at what pressure is the mean-free path of air at 300 Kelvin? So roughly the temperature of this room. Shorter than 0.1 centimeters. And the second part of this is longer than 100 centimeters. And I'm going to give you the diameter of an air molecule as d times 10 to the minus 10 meters. Okay, so it's just a kind of ballpark calculation. What I'd like you to do is take what we've just talked about, and for air at 300 Kelvin, take the diameter of your air molecule at about 3 angstroms, and just quickly plug it into our mean-free path expression, which I have erased, not very clever, and tell me what pressure we would be talking about if we've got a mean-free path that's less than 0.01 centimeters and greater than 100 centimeters. Okay. Is that a go with your neighbor? Then we're going to, we've done that, turn our attention to specific needs. So I'm going to give you 3 or 4 minutes on this one.
Don't worry about it.
And have, well, no, just like give the V and then, okay, you mean the number of molecules. Well, wait, NRT also has that, you're just gonna use the key that just goes, EV equals KB and well, it's not NRT, it's from KB. It's not from carbon, it's not DHK. Or sorry, it's not, it's KB or like KB. You know it.
That's close Oh, so this is like the flow of gas. What this equation is about. Mean free time. Average mass times grams per mole and 1 mole Avogadro's number. so n when n is the mass of it,
And it's amount of things.
yeah. So would it be the mass of the thing times the grams per mole of the thing times the number of moles in the mole of the thing, so the number of things. But I don't know if you have all the information. So maybe not.
Okay, I'm just gonna get n over v first.
Okay, but how are you finding n?
Oh, I'm not even gonna, I'm just by finding n over v. And then to get what n is, I think you have to, I don't know, arrange pv equals nRt somehow to get n over v.
Okay, I got you. Oh no, you're right. That's good. Because what you can do is calculate the length.
Bad boy.
So I guess the goal is first determine whether you treat it as a fluid or a gas, and then solve for pressure for you. Because right, if it's a fluid, you would use like.
No, you don't need to because they already tell you what the mean pouch is. So you're figuring out if they give you the pouch. You don't need it.
Well, because right, we have to find lambda, which is like that is
You're not finding it. You're finding pressure.
right. But in order to find pressure, you have to know whether you treat it as.
But they give you it. If it's shorter than this, you know what length it is.
It's shorter. That isn't that deep. 0.01 standard.
You know, I think it's I thought it was the path.
Right, because don't you have like sigma equals pi d squared? So then 1/2
No,
equals.
D is the air. No, it's like the air.
Okay,
D is
10
times
seconds.
10 to the negative 10. Lambda is 0.01 or 100, depending on which subset you're solving.
Oh, okay. Where's that?
So you don't actually
All right.
unless
So-
I misunderstood this.
Okay.
Quick look at this problem. So just setting it in context was this issue of when we can treat things as fluids and when we can treat them as maybe individual constituents.
No, I think
The main
you're right.
quantitative calculation one has to do is figure out what pressure corresponds to a meter path that, let's say, is 0.01 centimeters below or 100 centimeters and above with the parameters that were given. So given what we have on our mean-free path, very simple formula over on the left-hand side, apparently we don't have some key information, but how can we work around that? Very straightforward workaround. We're trying to figure out some relationship between mean-free path and pressure. How do we get that from what we've given already for mean-free path?
You find the density using the path equation, and then you rewrite the ideal gas equation to include number of molecules and I think Avogadro's number, and then you rewrite the part of ideal gas equation in order to
Really big. I think there's probably a lot of
incorporate density, particle density into it, and then find pressure from there.
Okay. Right. So obviously we need to recast this in terms of things that we know. So what do we know? Ideal gas equation.
Okay.
IGP dV N T.
Okay.
So I can presumably write this as N over V equals P over RT. So that's, I think, what you said. So this is in a molar basis. Actually, I realized when you asked the question, what's big N, I should have been more careful in my answer here, because we're really talking about the number of constituents. So I can also write this as N over V equals P over KT. So the usual switch with R and K and N, big N and little n. So there we go. So now all we need to do is work with this over here. Okay, and at this point, we don't have a whole lot to do, to be honest. So sigma cross-sectional area, just erased, but it is pi d squared. We know d, so we know the cross-sectional area. That's fine. Turns out to be about 3 times 10 to the minus 19 meters squared. That number makes sense. Yeah, sure. Obviously, I've got a diameter that's a few angstroms in my cross-sectional area. Just pi times d squared, so that makes sense. So we know that. Maybe another thing to just be aware of. If I know Boltzmann constant, and I'm talking about 300 Kelvin, KT in this case is around 4 times 10 to the minus 21 joules. If you want to keep in mind